In the last class, we looked at the procedure to evaluate information of a Markov source with arbitrary memory based on conditional information measures. Today, we will look at the evaluation of information of a Markov source with arbitrary memory based on joint information. In order to do that, let me take a simple example. Let us assume that I have a message Vi formed of symbols of length n. Previously, we had studied messages of length 1 only. So, let us consider messages of length n. This Si1, Si2, Sin, each of this can come from this Markov source with arbitrary memory whose alphabet is S1 to Sq. Now, I am interested in evaluating the information which is there in this message given by Vi. So, on an average, the information in this message of length n can be evaluated by this expression out here. This will be bits per message. Now, if I am interested in finding out the information per symbol, then HNS is defined as 1 by n of HV. So, we can say this is by definition, and this is nothing but equal to 1 by n joint information. Now, we had also seen last time that I can write HNS is equal to this quantity if I assume that all the symbols which constitute a message of length n are independent. In that case, HNS turns out to be same as HS. But if the symbols in this messages are not independent, then I can write a very generic expression for HNS, which is nothing but an average information per symbol in that message will be given by this expression out here, and that is 1 by n j summation j equal to 1 to n FJS. This we had seen last time. We had also seen that FNS is a monotonically decreasing function of n. Today what we will try to prove first is that HNS also is a monotonically decreasing function of n. In order to do that, let me state the theorem first. The theorem says if H of V is the amount of information for a message of length n, then the amount of information per symbol defined by HNS is equal to HV by n is monotonically decreasing. This is the first result which we will try to prove, and we further have that limit of n tending to infinity of Hn s will be equal to H infinity s. H infinity s was the entropy which we defined for a Markov source, and this is nothing but equal to limit of n tending to infinity of Fn s. So, we will show that both the limits are equal to H infinity s. So, let us try to prove this theorem. HV by definition is equal to n times Hn s. So, this is equal to H of S1 plus H of S2 given S1 plus H of Sn given Sn minus 1 up to S1. Now, we have seen last time that each of this quantity out here is related by this relationship. The additional information which I get at nth instant is less than the additional information which I get at n minus 1 instant, and this way I can continue up to the time instant 1. So, based on this relationship which we had derived last time, which is equivalent to Fns less than equal to Fn minus 1s, which we had proved that this is monotonically decreasing function of n, and limit of this is equal to H infinity s, and that was defined as entropy of a Markov source. Based on this relationship out here, I can write that this expression out here is greater than or equal to n times H of Sn minus 1 up to S1. Therefore, Hn s, which is nothing but Hv divided by n, is greater than or equal to H of Sn given Sn minus 1 S1, and that is nothing but by definition Fn s. This we had seen, this definition of Fn s is equal to this we had seen last time. Now, H of V is equal to H of S1, S2 up to Sn. This entropy, joint entropy, can be broken up as H of S1, S2 to n minus 1, joint information which I have from n minus 1 symbols, plus the additional information which I get from nth symbol . So, this relationship can be written like this. Now, from this relationship and this relationship, I can write n of Hn s is equal to n minus 1 H of n minus 1 s plus Fn s. Now, we have just seen that Fn s is always less than Fn s is always less than equal to Hn s. So, from this I can write n minus 1 Hn minus 1 S plus Hn S. Now, just trying to simplify this expression, we will get n minus 1 Hn S is less than equal to n minus 1 H of n minus 1 S, which implies Hn S is less than equal to Hn minus 1 S. So, I can proceed like this and show that this is less than equal to H1 S. Now, since HNS is always greater than or equal to 0 and HNS monotonically decreases with n, it follows that this quantity should converge to a limit as n tends to infinity. Let us try to find out what is the value of HNS as n tends to infinity. So, limit of n tending to infinity of HNS would be limit of n tending to infinity of 1 by n summation f j s j is equal to 1 to n. Now, we know that as n tends to infinity, f j s, because it is monotonic decreasing function of n, converges to h infinity s. Therefore, this is nothing but 1 by n times h infinity s, and this is equal to h infinity s. So, what we have proved that both HNS and FNS converge to the same limit which is given by h infinity s, and this is nothing but the entropy of a Markov source with arbitrary memory. But this condition is also valid, which we proved HNS is always greater than equal to FNS. What this implies that HNS is a worse approximation to the actual amount of information h infinity s, but the advantage of HNS is its simplicity in evaluation. So, with this result, let us proceed ahead and solve an example which will help us to understand and appreciate the material which we have covered so far. So, I'll try to explain whatever we have done so far in relation to a Markov process with the help of an example. Let us assume I have an example given here. I have a binary source 0 and 1, and this binary source is ergodic second order Markov source, and this conditional probabilities have been specified. Probability of 0 given 0 0 is 0.8, and other transitional probabilities have been specified. We had a look at this example earlier too. Now, the first thing is to draw a state diagram for this ergodic second order Markov source, and to do that, the state diagram for that is given as follows. We had also had a look at this state diagram earlier in the course of our lecture. Now, the first problem is how large is the amount of information of a trigram originating from this information source. What I mean by this statement is that if I look at the messages which are being emitted from this source as messages of length 3, then what is the amount of information which is contained in that message. So, let us try to evaluate this. In order to evaluate this, what I have to do is basically to calculate the amount of information per trigram. The probabilities of the trigrams are determined first. Now, in order to do this, what I have to find out is probability of 0, 0, 0. This is nothing but probability of emitting 0 given I was in the state 0, 0, and what is the probability of being in the state 0, 0. Now, we had earlier calculated the probabilities of the states as probability of 0, 0 equal to probability of 1, 1 is equal to 5 by 14, and probability of 0, 1 equal to probability of 1, 0 is equal to 1 by 7. We have had a look at the procedure to calculate these probabilities. Assuming that these probabilities have been calculated earlier, let us try to calculate the probability of the messages of length 3. So, the different combinations which I can have of the messages of length 3 would be like this. So, first one is probability of 0, 0 would be given by this, next would be probability of 0, 0, 1, this would be given by what is the probability of emission of 1 given I was in the state 0, 0 and probability of 0, 0. When I am writing this 0, 0, 0, 0, 0, 1, I assume that this is the latest symbol and these are the previous symbol. So, this is the furthest away from this symbol. So, to find out probability of 0, 0, 1 is that I have to find out what is the transition probability 1 given 0, 0 and of being in the state 0, 0. So, I have to evaluate this all these probabilities. Now, probability of 0, 1, 0 is again probability of 0 given I was in state 0, 1 multiplied by probability of 0, 1. Now, this is the quantity probability of 0 given 0, 0 is 8 by 10 because 0.8 has been given to us. This is the probability which has been given to us, and probability of 0, 0 we have calculated, that is nothing but 5 by 14. So, this turns out to be 4 by 14. Similarly, this quantity turns out to be 5 by 14 multiplied by 2 by 10 is equal to 1 by 14. This quantity turns out to be 1 by 14. So, based on this idea, I can calculate the probabilities of 0, 1, 1, that turns out to be 1 by 14, probability of 1, 0, 0 is again 1 by 14, probability of 1, 0, 1 is equal to 1 by 14, probability of 1, 1, 0 is 1 by 14, and finally probability of 1, 1, 1 is equal to 4 by 14. Once I have this probabilities, I can use the expression for the calculation of the entropy and calculate the entropy or the information in the trigram as equal to minus twice 4 into 14 log of 4 by 14 minus 6 times 1 by 14 log of 1 by 14, and this turns out to be 2.67 bits per trigram. So, for the example under consideration, we have for the messages of length 3, the information in those messages is 2.67 bits per message. The message is nothing but a trigram, that is symbols of length 3. Now, the next question is, once I know this is basically what we are calculating is h of n s, and in our case this n was nothing but equal to, sorry, yeah, now the next question is that once I know the message in a trigram, then determine the amount of information per symbol, which is denoted by H3S. Now, if I want to calculate H3S, it is very simple. Since I know my H of trigram was equal to 2.67 bits per trigram, this is nothing but HV, and H3S 1 by 3 H of trigram, and this is nothing but 0.89 bits per symbol. Now, the next question is, I have calculated, if I were to reduce these messages from the length 3 to length 2, then what happens to the amount of information? To answer that question, let us solve this. So, next what I am interested is, how large is the amount of information of a bigram, hence determine H2S. So, the probabilities of the bigrams are identical to the probabilities of the states. And since we have calculated the probability of the states earlier, so we can say so that information from the bigram would be minus twice 5 by 14 log of 5 by 14 minus twice 1 by 7 log of 1 by 7, and this turns out to be 1.86 bits per bigram. This is your again HV, here the message is of length 2, and hence H2S, which is nothing but half H of bigram, is equal to 0.93 bit per symbol. Now, let us look at the messages of length 1. So, if I look at the messages of length 1, then how large is H1S? To calculate this, I should know the probabilities of P0 and P1. Now, once I know the probability of 0 and probability of 1, I can calculate H1S. We have seen basically how to calculate the probability of 0 and probability of 1 for this example earlier. So, we had seen that probability of 0 is equal to probability of 1, and that turns out to be equal to half. So, from this I get H1 S is equal to minus half log half minus half log half, and that is equal to 1 bit per symbol. So, now we have calculated H3S, H2S and H1S. The value of H3S we got was 0.89 bits per symbol, value of H2S we got was 0.93 bits per symbol, and value of H1 was 1 bit per second, 1 bit per symbol, sorry. So, what this means that as I keep on increasing n, the value monotonically decreases. From 1 I have reached up to 0.89. So, the final limit of H3 of HNS would be H infinity S. Now, if I were interested in to calculate F1 S, F2 S and F3 S, let us try to evaluate this. So, the conditional amount of information in the event that n minus 1 preceding symbols are known is denoted by FNS. So, what I am interested is to determine F1S, F2S and F3S. We have derived that NHNS is equal to n minus 1 Hn minus 1 S plus Fn S. Now, if I want to calculate F1 S, since I know H1 from F1S is nothing but H1S, and that is 1 bit per symbol. F2S from this relationship I will get as twice H2S minus H1S. Now, I know H2S and H1 as I have calculated earlier. So, this turns out to be 0.86 bit per symbol, and finally, my F3S is equal to thrice H3S minus twice H2S, and this comes out to be 0.81 bit per symbol. Now, what we have observed that for an increasing value of n, FNS will be determined by the transition probabilities of which the value is dependent on an increasing number of preceding symbols. So, the uncertainty therefore decreases, and therefore, FNS will also decrease. Now, in our case, if we try to calculate F4S, F4S will turn out to be same as F3S because Markov source is order second. So, the only the two preceding symbols now have an influence on the value of the transition probabilities. Therefore, FNS will be equal to F3S for n greater than or equal to 3. Now, another interesting result is Fns does not change beyond F3s, but what happens to H4s? If you look at H4s calculation, then you will find that the value of H4s is smaller than that of H3s, because with the calculation of HNS, the first two symbols of the message remain of influence. It is also clear that this influence does decrease. However, so that HNS is a monotonic decreasing function of n with a limit value. So, if you take the limit of HNS n tending to infinity, you will get as same as F3s, because F3s is nothing but limit of n tending to infinity of Fn s, and because our source is a second order Markov source, Fns is for n greater than equal to 3 is same as F3s. Now, if you plot the values of HNS and Fns as function of n, what you will get is this graph. It is interesting to examine this graph. On the x-axis I have the increasing value of n, on the y-axis I have plotted Fns or HNS. If you look at the plot of Fns for n equal to 1, we found out to be value to be of F1s was 1, for Fns for n equal to 2 was lower than that, and for F3 was still lower, but F4s, F5s is all stabilized to the value of F3s. But this is not true of HNS. HNS, though it is monotonically decreasing function, but as I keep on going beyond n greater than 3, you will find that HNS keeps on decreasing, and finally it approaches the value of F3s, and that is equal to 0.81. So, what I would say that entropy of this source which we have considered is 0.81 bits per symbol. Let us take another example to understand the concepts in a much better way. Assume that the various values of FJS are known for 26 different symbols. This could be an example of English literature. So, let us assume that I know F1 is equal to 4.15 bits per symbol. Now, from this I know H1 is directly equal to F1, so that will be equal to 4.15 bits. If I can calculate F2, which are calculation of all this F1, F2, F3 is based on the conditional information measures. So, F2 if I can calculate, and if I know it is 2.99, then I can calculate H2, which is equal to 1 by 2 F1 plus F2, and that turns out to be 3.75. So, I can keep on calculating like this F1, F2, F3, F4 up to F8, and similarly I can calculate the values for H8 from Fs. If you look at this values of Fn and Hn, there is an interesting result. You will find that always Hn is larger than Fn. That is the one point which you have to notice. Another is Fn is always a monotonically decreasing function of n. Similarly, you will find that Hn is monotonically decreasing function of n. Now, if you look at the way this Fn decreases much faster than Hn. When I reach F8, the value for entropy turns out to be 1.60 bits per symbol, whereas H8 is 2.25 bits per symbol. If you continue this process, then you will find that H infinity s stabilizes or converges to a value of 1.50 bits per symbol. HNS will also converge to the same value 1 bits per symbol, but the convergence rate will be slower than that for Fn. And if I were to find out what is the maximum value which I can get of an information from this source which consists of 26 different symbols, the value will be obviously equal to log of 26. That will happen when I assume the symbols are all independent, and that turns out to be 4.7 bits per symbol. What I want to convey from this example is that if I take a source which consists of 26 different symbols, then the entropy of that source, based on the assumption that all the symbols are equiprobable, I will get that entropy to be equal to 4.70 bits per symbol. But if I look at that source with a memory, then the entropy turns out to be much lower than 4.70 bits, and it is equal to 1.50 bits per symbol. So there is a lot of discrepancy between these two entropy. Now, to get a better feel, we will take one more example before we conclude our discussions on the modeling of these sources from the information point of view. Let us take another example. Let me assume that I have a source which emits 3 symbols S1, S2, S3. This source is a stationary, and I also assume that this source is a first order Markov source. It has been given to me that the transition probabilities of a symbol Si to a symbol Sj with I not equal to j are all equal to p by 2. P is a variable. So what it means is that probability of Sj given Si is equal to p by 2 for I not equal to j. Now let us try to calculate the different values for information measures which we have studied so far. The first thing that is to be done before we do the calculation is to draw the state diagram for this source. The state diagram for the source will give us all the information which is essential for us to calculate all the transition probabilities. So if I take the state diagram for this, would be something like this. So the state diagram would be given by this. This is a state diagram for the source under discussion. Since we have this source which is a Markov source of order 1, and there are 3 symbols, we have 3 states. These 3 states are identical to the 3 symbols. So S1 is equal to small s1, capital S2, which is denotes the state, is same as the symbol S2, and the third state S3 is identical to the symbol S3. Now it has been given to us that probability of Sj given Si is equal to p by 2 for I not equal to j. So if I take an example for this state, then the probability going from this to this is p by 2, and from here to here is p by 2. So the probability of being in the same state would be calculated by addition of this p by 2 plus p by 2, that comes out to p. 1 minus p would be the probability of remaining in this state. So similarly I can calculate for state S2 and S3, and this would be the state diagram which I get for the source under discussion. Now next is basically what I am interested is to calculate the probabilities of the symbols S1, S2 and S3. Now, since the states and the symbols in this example are the same, calculation of the probabilities of the symbol is equivalent to calculation of the probabilities of the states S1, S2 and S3, and we had seen how to do that. Let us try to calculate these probabilities. So, the probabilities of symbols S1, S2 and S3, or in other words the probabilities of the state capital S1, capital S2 and S3 follow from this equation. Probability of S1 would be what is the probability of emission of S1 when I am state S1 and multiplied by the probability of the state S1 itself, plus what is the probability of emission of S1 when I am state S2 multiplied by probability of S2 itself. So, this would be the expression which I get for calculation of the probability of the symbol S1, and in this case it is equivalent to calculation of probability of the state S1, that is capital S1. And similarly this equation follow for symbol S2 and symbol S3, and I know that probability of S1 plus probability of S2 plus probability of S3 is equal to 1. Therefore, if I substitute these values, if I solve all this equation, what I will get is this result. Probability of S1 is equal to probability of S2 is probability of S3 is equal to 1/3. Now, because of the symmetry of the state diagram, this result was expected. So, the symmetry suggests that each state will occur with equal probability. Now, during the course of our study of Markov source, we also talked about the information associated with the arbitrary transitions. In order to understand that concept in a better way, let us try to find out the amount of information with respect to an arbitrary transition for this example under discussion. So, I am interested in the calculation of information with respect to an arbitrary transition. What I mean by that, I am interested in calculating average information of S2 given S1. In the light of our earlier discussion, this Sj is equivalent to S2j and Si is equivalent to S1i. So, by definition H of S2 given S1 would be probability of Si Sj joint probability multiplied by what is the information which I get when there is a transition from Si to Sj. The amount of information which I get from one transition, from one particular transition Si to Sj is minus log of P Sj given Si, and the average value would be this. So, if I try to simplify this value, I will get as this is equal to probability of Si probability of Sj given Si log of probability of Sj given Si. Now, this I can simplify as I can remove probability of Si outside the bracket log of probability of Sj given Si. this can be simplified because probability of SIs are all equiprobable. So, it will be 3 times 1 by third minus 2 p by 2 log of p by 2 minus 1 minus p log of 1 minus p. This is the value which I will get when I am in a particular state, and since all the probabilities of the states are equiprobable, I have to just multiply it by 3, and if I simplify this expression turns out to be p minus p log p minus 1 minus p log 1 minus p bits per symbol. If you plot this, the plot of this expression as a function of p can be, this is familiar expression which we get, this is the entropy function we have. So, this is also the entropy of a binary source, and this I can plot as a straight line. So, entropy, the amount of information with respect to an arbitrary transition is sum of 2 functions. This is the entropy function, and another is a linear function. So, we can plot this as this would be the result for my entropy function, and that is nothing but minus p log p minus 1 minus p log 1 minus p. These values will range from 0 to 1, and this will be my p. So, my h of S2 given S1 would be the sum of this, and that will turn out to be something like this. So, if you look at this additional information, this is the graph for this. Now, this graph shows that there is there is a peak out here. Let us try to evaluate what is the value of this maximum, what is the maximum value which this achieves, and for what value of p it achieves. So, to determine the value of p for which this amount of information, that is h of S2 given S1 achieves a maximum, it is not very difficult. So, determine the value of p for which this amount of information achieves a maximum is given by derivative of h of S2 given S1 is equal to 0. So, now let us take the derivative of it, p minus p log p minus 1 minus p log of 1 minus p is equal to 0. This implies derivative of this is 1, derivative of p log p will be 1 by log 2 minus log p plus derivative of this quantity would be plus log of 1 minus p. This implies that log of 1 minus p upon p is equal to minus 1, which implies log of p over 1 minus p is equal to 1. Therefore, this implies that p over 1 minus p is equal to 2, and this implies that p is equal to 2 by 3. So, the maximum value of, so this is the value at which the maximum will occur. So, in this graph, this maximum value will occur for p equal to 2 by 3. This occurs at 0.5. Now, what is the maximum value? If we calculate that, maximum value, I have to evaluate that expression for p equal to 2/3, and if I substitute that, I get 2/3 log third, and this turns out to be log 3. This is equal to 1.58 bits per symbol. So, this is the maximum value which I get for this quantity, and this is the arbitrary transitions. Okay. Now, let us look at this graph, and if you look at this graph H2S, H of S2 given S1, for p equal to 0, I get this value to be 0. Now, this is expected because at this point p equal to 0, the source remains in the same state. Therefore, there is no uncertainty, and therefore, the amount of information is 0. When p is equal to 1, the source has an equal chance of coming into one of both other states from any given state, because probability of Sj given Si is equal to half in that case, and in that case the information, the transition information will be 1 bit. Now, when p is equal to 2/3, every transition has the same probability of occurring. Therefore, the source behaves as if there are 3 independent symbols. What it means that if a previous symbol is given, the uncertainty is not reduced, and therefore, H of S2 S1 turns out to be same as the entropy of the source when the source symbols are independent, and that is log 3 bits per symbol. So, with this we complete our discussions about the modeling of the sources from the information point of view. We have looked at different types of sources, which are memoryless, that is 0 memory, and the sources which have memory, and in that category we have considered a Markov source of arbitrary order. We have also looked at the calculations of the informations for this source. Now, with this base, we will go ahead and look at the coding aspect for these sources.